Hello, this is Mr. Precella discussing some trigonometry today. In our last session, we discussed right triangle trigonometry, and we defined the trig functions in terms of a right triangle, SOHCAHTOA, and we solved right triangles. And today we're going to look at some applications. Those are word problems involving this involving right triangles. And to get started, I'm going to give a little bit of terminology. Okay? If we have a horizontal, an angle that's measured from the horizontal upward is called the angle of elevation. So if it's up from the horizontal line of sight upward, angle of elevation, whereas an angle measured from that horizontal line of sight downward is called the angle of depression. Now, we're going to see some of this new terminology. Well, new to you, not new to the world of mathematics. As we do an example, problem number 1 says, this example here. Okay, the angle of a vertical tower is 74 feet long when the angle of elevation of the sun is 36 degrees. So here's the tower, and it's drawn. The angle of elevation, notice it's measured from the horizontal up. And notice this distance, the shadow here, 74 feet long. Find the height of the tower. So in this one, the right triangle is staring you in the face. There it is. And let's see, which side are we trying to figure out? We know this side here. It's not the hypotenuse that we want to know. If it says find the height of the tower, that would be this one right here. So let's call this some variable. I'm going to call this side H. I'm not going to go through an H for height. Maybe I should have put T for tower, but then it might look like a plus. So there's our right triangle, and looking at the data that's given, the 36 degrees and the 74 feet, and then taking into consideration what we want to find, H, which trig function, I'm thinking, is it sine, cosine, or tangent? Well, it's not the cosine or sine, because it doesn't involve the hypotenuse. Maybe by H, that's for, don't start thinking that stands for hypotenuse. Maybe I should have used a different variable, maybe just a y or something, but I've used H. This is going to use the tangent curve, isn't it? Or the tangent function, because we could write tangent 36.0 degrees equals opposite over adjacent. So H over 74.0. Now, multiply both sides by 74.0. And you're going to have to punch in 74.0 times tangent 36 degrees. Now, make sure your calculator is in the degree mode. And I'm punching in 74 tangent 36 degrees, and we get 53.764. They're cutting the power off here. 53.764. Now, how are we told to round it? 53 53.764 dot dot dot. It goes on and on. But it says to round to the nearest hundredth. So tenths, hundredths, you're going to write that as 53.76 feet. So the picture isn't exactly accurate because the tower isn't as tall as the shadow, but it sure looks like the tower's taller than longer than the shadow there. Okay? Let me see if I can find one where the picture's not already drawn for us. Well, the very next one. Problem number 2. Problem 2 says, suppose that you were you're headed toward a plateau 49 meters high. Oh, well, that sounds like the vertical part of the triangle. If the angle of elevation to the top of the plateau is 20 degrees, how far are you from the base of the plateau? Oh, well, heck, is this one pretty much just like the one we finished doing? Thinking it is, isn't it? We know the height of the plateau. You want to know how far are you from the base of the plateau? I'm just going to use x. I guess I could use d for distance, but I'm using an x there. And once again, which trig function is this one going to be? You're using this, that. That would be opposite over adjacent. It's another tangent. Tangent 20 degrees is 49 over x. Opposite over adjacent. Multiply both sides by x. And then divide both sides by tangent 20 degrees. See if you agree with that. 49 divided by tangent 20 degrees. That's what I'm going to have to punch into my calculator. I know it's sort of hard to tell. So I'm going to go 49 divided by tangent 20, 134.6263, 134.6263 dot dot dot. We're told to round to 2 decimal places. 1, 2. That'll be 134.63. Okay. We are looking at applications of right triangle trigonometry. Next one we'll do is number 3. This one is fairly involved. This one here, number 3. Okay. From a window, you'll see it. From a window 30 feet above the street, the angle of elevation to the top of the building is 52 degrees. It might be hard for you to read these. And so I'll draw the picture in a moment. And the angle of depression to the base of this building is 15 degrees. So you have the horizontal line of sight. Let me draw it like this. Here's that building. The angle of elevation to the top of the building is 52 degrees. The angle of depression to the bottom is 15 degrees. Okay. Now, there's this building here, and we're told that it's from a window 30 feet above the street. So this distance right here is 30 feet. So when I look at these triangles, there's several triangles here. If I look at the bottom one, we know this distance here is 30. So that's the triangle. I don't know if you can tell these colors. I've sort of outlined it in pink. That's the bottom triangle. Now, we want to know, find the height of the building across the street. So we want to know this whole height right here. What we know already is that this is 30 feet from here to here. As you can tell, that, see what's going on in that picture. Okay, this is 30 feet. So if we figured out this distance right here, if we knew that distance, let's call it y, all we need to do is, to get the height of the building, is add 30 plus y. So how the heck can we find this distance? This is what I'm calling y right here. Well, if we look just at this top triangle, there's just not enough information here. We have an angle and the opposite side, but in order to use a trig function, we need to know either that hypotenuse or this adjacent leg, one or the other, and we don't have either of those. So let's look at the bottom triangle. On the bottom triangle, we have an angle, and this would be what? Opposite? Well, that means we could either find the hypotenuse or this side right here. Well, I think it'd be best for us to find this side right here. I'm going to call this distance here x. Once we know this side here, then we're going to be able to find y without any trouble. So I'm using the bottom triangle, the pink triangle, using this angle. This would be opposite and adjacent. So I'll write tangent 15 degrees is opposite over adjacent. Divide both, multiply both sides by x, and then divide by tangent 15 degrees, and we have 30 over tangent 15 degrees. So I'm not going to round until the very end, okay? Clearing that. I'll punch in 30 divided by tangent 15, and it's showing 111.9615242. I'm not going to round to the very end, and I'm not going to have to punch in this number again. When I need it, I'll just use that second A and S key on the next stuff as I write. So we've now figured out this horizontal distance here. In terms of the top triangle, I'm now going to try to find y. I know x is 111.96 blah blah blah. So I'm going to say, okay, there goes the lights again. What's going on here? So looking at the top triangle, this is another tangent. I can say tangent 52 degrees is opposite over adjacent. So multiply both sides by that 111.96 blah blah blah. So, heck, there's that number already showing in my calculator. So I'm just going to go times tangent 52. I'm showing 143.3042 dot dot dot. How are we told to round? To the nearest whole number. So 143 feet. And if you punch that into my math lab, it's going to say wrong. What have I not done? Not what am I forgetting, I just haven't done it yet. Well, that's what I've just found is y. 143 feet. So the whole height of the building, I'll write it right here. The height would be 143 plus that additional 30. So the answer to the problem, 173 feet. Oh, sorry. We're cutting off top of the problem. Okay. So that's a very nice problem. Notice how we used the bottom triangle. We used it to find this distance here, so we could calculate that vertical distance. Okay. Just working some examples on applications of right triangles. Let me find another one for us to do. Keep going and do problem number 4 next, because I'm going to illustrate something on your calculator on this one. Problem 4. A tower that is 119 feet tall casts a shadow 120 feet. Find the angle of elevation of the sun to the nearest degree. Well, this one, I don't think it's going to be tricky for you to set up. Most of you can figure it out. It's going to be tangent. Tangent is opposite over adjacent. But here's the thing that's a little tricky. We've got to solve, this one, you're not solving for one of the sides, you're solving for one of the angles. So how do you use your calculator to solve for an angle? To get theta by itself, I guess we could go into a little detail and review inverse functions in your from algebra. But in order to get this theta by itself, you can't just divide by TAN. The thing that cancels out this theta will be inverse tangent. And you might recall seeing this, or you've seen it somewhere in an algebra class, something called inverse functions, denoted with the little -1. We won't actually define inverse functions in this course formally until the very end of the semester, or very close to the end, the last month, let's say. Now to punch this into your calculator, and you'll see, here's the tangent key. It's that little yellow tangent. So if you're trying to solve for an angle, you're not going to just press tangent. To get to that yellow key, you're going to have to press second tangent. Now, if I move this down a little, I'm going to go second tangent. That acts as a little tangent with the -1, and then 119 divided by 120. So if you're going to be solving for an angle theta, or whatever you're denoting the angles with, you have to use the inverse functions. The second sine, second cosine, second tangent. And this is 44.7602 dot, dot, dot. How are we told to round it to the nearest degree? So just 45 degrees. Now, I'm just doing some examples here over applications of inverse functions. This next one has a picture drawn and a lot of words. Let's see. The altitude of a mountain peak is measured as shown in the figure to the right. At an altitude of 14,558 feet on a different mountain, the straight line distance. Oh, okay. Hey, this seems sort of like the problem that we had earlier, didn't it? With the two buildings. So the altitude of a mountain peak is measured as shown at an altitude of 14,558 feet. So they're up 14,558 feet when they take this reading. The straight line distance from here to the peak is 27.1343 miles. And the peak's angle of elevation is 5.51 degrees. Approximate the height of the mountain. Well, this problem is a little trickier than at first glance. Why? Because this distance here is in terms of feet, and this distance here is in terms of miles. And we want our answer to be in terms of feet. So we're going to need to convert these miles to feet. So 1 mile is 5,280 feet. Okay? How many of y'all knew that approximation? So the 27.1343 miles, I'm going to multiply by 1. I'm going to write 1 mile, 5,280 feet. So basically, to convert from miles to feet, you just multiply by 5,280. So 27.1343 times 5,280 . Okay. And I'm not going to round until the very end. 143,269.104 feet. So, actually, I think this one, that's the only tricky part about this one. If we want to find the rest of this height here, look at the triangle we have. We don't know this side here, but we know the hypotenuse. So I'm just going to call this vertical y. And theta is 5.51 degrees. Let me blow that triangle up. So I'm looking for y. This is that distance, the 27.13 feet. And this is 5.51 degrees. So this would be an example of sine. Sine 5.51 degrees is opposite over hypotenuse. So multiply both sides by that 143,269.104 sine 5.51 degrees. I don't think I cleared out my calculator. That long number is still showing. So I'm just going to say times sine, 5.51. So y, 13,756.62493 adding, boy, this is getting kind of these lights keep going on in the room I'm using right now. So I need to add the 14,588, no, 558. So just adding plus 14,558. And I get 28,314.6. We're told to round this to the nearest foot. So 28,300 and, would y'all say 15? Yeah, 28,315 feet. That's right. Any questions? Following this, okay. These are some nice little applications of right triangle trigonometry. Now, little something new. Navigation. There are two ways that direction can be stated. One way is the single angle method. If you were told a ship is traveling on a bearing of 130 degrees, normally in this class, when we measure angles in any math class, we're measuring from the x-axis, except with navigation. With navigation, you're measuring from the y-axis. With the single angle method, you always start measuring at due north, and you move in a clockwise direction. Okay, due north, move in a clockwise direction. If you had a ship that was traveling on a bearing of 130 degrees, you start here, move 130 degrees, well, due east would be 90 degrees, so another 40 degrees. If a ship is traveling on a bearing of 130 degrees, that ship is going in a southeasterly direction. That's called the single angle method. There's another way you could state direction, and that's using the, notice this angle here could be anything from 0 to, I guess, 360, probably not including 360, because you'd be back at due north. Another way is the direction and acute angle method. With the single angle method, you always start measuring at due north. With this other direction, this other measuring method, you start off by telling, okay, do you start at north or south? North or south, followed by an acute angle. An acute angle is one that's less than 90 degrees, and then east or west. This angle here will always be smaller than 90 degrees. You can't have an angle with this method, you can't have an angle of 130 degrees. So if a ship were traveling on a bearing of, let's say south, 32 degrees west. With this method, it's telling you southwest. It's going in a southwesterly direction. Whereas the single angle method, you sort of have to think it through to decide, okay, it's going northeast, southeast or something. So with this method, it tells you start at due south, so down here, and then move 32 degrees towards the west. This angle right here is the 32-degree angle. Okay. So that is the direction and acute angle method. Now let's do a problem. I have a couple of examples I want to do with this stuff here. Let's see. Get us some. Here's the problem we're going to be working. It's number 6. Yeah. No, the number doesn't matter, okay? It's number 6 on the sheet of paper I'm working out here. So, let's see, problem 6. A plane flies 1.3 hours on a bearing of 20 degrees. So notice they're drawing the picture out here. You start at due north and move just 20 degrees in a clockwise direction. It then flies, so it flew 1.3 hours at 150 miles an hour. So you can figure out this distance here just by multiplying 1.3 times 150. 1.3 times 150. Ooh. 195. So this side right here is 195 miles. It then turns and flies 3.6 hours at the same speed, 150 miles an hour, on a bearing of 110. So notice how they drew the triangle. Once you got here, they drew a due north and start and move 110 degrees in a clockwise direction. So to get this side here, let me write out, since there's room, what I'm doing to get this side. You take the 3.6 hours, multiply it by 150 miles per hour. So 3.6 times 150, 540. How far is the plane from its starting point? But do we need any trigonometry on this? Well, no. Provided this is the right triangle. Could you convince yourself it was the right triangle? Where does it look like the 90-degree angle is? Right there? A lot of times students don't do what I'm about to do, but you should really make a habit. You need to make sure that this is really a right triangle, and if you drew this vertical line and continue, then you'd have 70 degrees. 110 plus 70 would get you a straight line, and then this angle and that angle would be alternate interior angles. If you looked at two parallel lines being cut by a transversal, if you remember a little bit of geometry, or a little geometry, so 70 and 20, yeah, that's going to give you 90 degrees. So once you know that this is a right triangle, it's going to fall out real easy. Do we need to do any trigonometry? Well, no, we can just use the Pythagorean theorem on that one, can't we? So let's see, I'll just do it right here. It is called C. So C squared is 195 squared plus 540 squared. So I'm going to have to punch that into my calculator and take a square root. So the square root of 195 squared plus 540 squared. See that? 190 squared of 195 squared plus 540 squared. 574.12977. How are we told to round it? To the nearest whole number, so 574 miles. Just a Pythagorean theorem problem. It's Now, let's see. Let's do one where the picture isn't drawn. When the picture isn't drawn for you, it takes a little bit more thought. Okay? So, this is problem number 7. Well, again, the exact number doesn't matter. I keep mentioning the problem number, but it's just, this is the number of example I'm doing. Problem 7. Okay. Big old pink 574. 2 ships leave a port at the same time. The first ship sails on a bearing of 55 degrees at 26 knots. That's nautical miles per hour. And the second on a bearing of 145 degrees at 24 knots. How far apart are they after 1.5 hours? Neglect the curvature of the Earth. I'm sure all of y'all were worrying about that curvature of the Earth factor, but we're going to neglect that. So, I'll just start off. 2 ships leave a port at the same time. So, I'm going to put a dot right here. I'm also going to very lightly draw my north, south, east, west grid lines. The first ship sails on a bearing of 55 degrees. That means you start at the due north and move 55 degrees from the due north, okay, in a clockwise direction. It's sailing at 26 nautical miles per hour. The second ship on a bearing of 145 degrees. So you start at due north, move 145 degrees. So that's going to be in a southeasterly direction. So if this is 145 degrees from here to here, I bet most of y'all can, it's not hard to figure out that this is 90 degrees right there. If from here to the red line is 145, and from here to the green line is 55, 145 minus 55 is going to give us 90 degrees. So 2 ships are leaving at the same time. The green one is going faster. It's 26 knots versus 24 knots. How far apart are they after 1.5 hours? Well, there's a right angle here, so we're looking for this hypotenuse. Well, let's just find the length of the sides. This green side, 26 knots times 1.5. Let's see, that would be 26 plus half of 26. 26 plus 13, 39. So this distance here is 39. And here, the red one, it'd be 24 times 1.5. 24 times 1.5, that'd be 24 plus half of 24, 24 plus 12, 36. And at that point, it's just another Pythagorean theorem problem. A squared plus B squared, C squared. Can y'all see this? So C is going to be the square root of all of that. So I've misplaced my calculator, believe it or not. Here it is. So square root of 39 squared plus 36 squared. Square root of 39 squared plus 36 squared. 53.0754 ... How are we told to round it to the nearest nautical mile? So this is going to be 53. Just doing some examples of applications of right triangle trigonometry. Ooh, it's all crooked up there, isn't it? I'm sorry about that. Let me see if there's another one here we have time to do. How long have we been going at this? I'm going to do this one here because it's another navigation problem. So let's do that one on top. It's number 8. There. Okay. The bearing from city A to city B is north 54 degrees east. So that means it's in a northeasterly direction. The bearing from city B to city C is in a southeast 36 degrees. An automobile driven at 65 miles an hour takes 1.6 hours to drive from city A to city B, and it takes 1.8 hours to drive from city B to city C. Find the distance from city A to city C, and once again, we are going to neglect the curvature of the earth. Okay, so I'm just going to start right here. Here's city A. And real light, north, south, east, west. Oh, let's see. Let me do this so there's not so much showing through. There. Is that easier to see? Well, maybe not. Okay, so the bearing from city A to city B is north 54 degrees east. So you start at due north and move 54 degrees east. Okay. Then the bearing from, okay, so that's city B. The bearing from city B to city C is southeast, in the southeast direction, south 36 degrees east. That means you start at due south and move 36 degrees towards the east. So from here to here is 36. Now if we think of these as two parallel lines being cut by a transversal, this angle and this angle are both 54 degrees. So, yeah, this is a right triangle. This is going to be a right triangle. From there to there. Now, which side is longer? Let's see. It takes 1.6 hours to drive from A to B. It takes 1.8. So this blue side is a little bit longer. Try to draw it like that. So there. So here's our triangle. Now let's label the sides. Well, this first side, it was 1.6 hours going at 65 miles an hour. So 65 times 1.6. This side right here is 104. Again, the way I got that 104 was 65 times 1.6. Similarly, the blue side, 65 times 1.8. It's 117. Again, 65 miles an hour times 1.8. And find the distance from A to C. Ooh, I didn't label that city C. Well, this is the distance as the bird flies. distance, or okay, straight line distance. So another Pythagorean theorem. This is the hypotenuse. So c squared is 104 squared plus 117 squared. So I'm going to have to take the square root of that. The square root of 104 squared plus 117 squared. Enter 156.5407. We're told to round to the nearest mile, so that's going to be a 156 or 157. Which one? 157? Okay. Any problems with that? So, one other thing I want to do, one more problem. Let's see. I want to do 10, and then if we have time, I'll go back and do number 9. Okay, I'm going to do problem 10 first, just because I'm not sure that we've seen any. Up until this point, all of our angles have just been stated as degrees or decimal degrees, maybe 35.7 degrees. But angles can be broken up into minutes just like an hour can. 1 hour is 60 minutes. 1 degree can be broken up into 60 minutes, and the minutes are denoted with a little mark like that. And just like we say 1 minute is 60 seconds, these minutes here we can break up as 60 seconds. On this problem number 10, sorry. This problem number 10, so 1 degree is 60 minutes, and we denote minutes with 1 little mark. 1 minute is 60 seconds, just like with the clock, just like with time. An hour is 60 minutes, a minute is 60 seconds. Only difference, a degree, 60 minutes, a minute, 60 seconds. A 15.5 meter fire truck ladder is leaning against a wall. Find the distance d the ladder goes up the wall if the ladder makes an angle of 35 degrees 29 minutes with the horizontal. So here's our big, I'm just going to draw the picture real large. 35 degrees 29 minutes. This is 15.5. We want to know d. Well, in a moment I'll show you how to punch in this 35 degrees 29 minutes in your calculator. But the trig function using this angle, that would be opposite and hypotenuse. So that's going to be sine. So I'm going to write sine 35 degrees 29 minutes equals opposite over over hypotenuse. So multiply both sides by 15.5. So here's what we're going to have to punch into our calculator. 15.5 times sine 35 degrees 29 minutes. So let me clear out all of that. Now there's a couple of ways you can punch this in. One way is just to say 15.5 sine 35 That's angle. Do y'all see a second angle key right there? It's hard to see, isn't it? It's shared on my calculator. It's with matrix. It says angle. I go second angle, and the very first thing is a degree mark. So enter 29 second angle. The second thing is the minute mark. So that's, your calculator is some way for you to enter degrees in minutes. So we're getting 8.997224775. Oh, that's a good way of showing it there. Again, the key that I was doing, 15.5 sine 35 second angle 1, that gets the degrees, 29 second angle, and on this TI-83 that I'm using, the angle key shares with the matrix key. 2 gets the minutes. Now if you don't want to do that, you could just do a little bit of arithmetic to convert the 29 minutes to degrees. If someone told you, if you saw 120 minutes, how would you convert that to hours? I bet all of you know. Y'all can all do that. 120 minutes, you can do it in your head. Divide by 60 to get hours. That's what you could have done. You could have just put this 15.5 sine 35. Now we're just going to convert the 29 degrees to minutes. Excuse me, the 29 minutes to degrees by saying plus, go to minutes divided by 60. Just like if you were converting, oh, there it goes. I don't think it's ever been like this before. Through my men, they just want to. So, 2 ways you could enter those degrees in minutes. Either way, you're going to get the same answer. We're told round to the nearest hundredth. So 8.99, that's going to be a 9.00. Y'all see what I did there? And you know what? We have time. Just barely. If I rush through, I think I'll be able to get one more done. Let me do this one. Oh, wait. This one here. Ooh, not the 157. To measure a stone face carved on the side of the mountain, 2 sidings 800 feet from the base of a mountain are taken. Oh, this is a pretty involved one. If the angle of elevation to the bottom of the face is 34 degrees and the angle of elevation to the top is 37 degrees, what's the height of the face? So here's the face. Okay, it's on the side of a mountain. The face is out there. To measure a stone face, 2 sidings 800 feet from the base of the mountain. So this is 800 feet. The angle of elevation to the bottom is 34 degrees. The angle of elevation to the top is 39 degrees. What's the height of the stone face? By the height of the stone face, I think of that more as length. What they want to know is this distance here. Okay? How tall is that stone face? Well, to do this, we're going to use 2 different angles, triangles. I'm going to first find this distance here, and then I'm going to find that distance. And then to get this, the height of the face or the length of the face, we're going to subtract those 2 numbers. So I'm first looking at the completely black triangle. That's the smaller one, the one that has 34 degrees here, and 800. I'm going to call this distance right here A. I'm going to find A using which trig function? Well, tangent. Tangent, 34 degrees is opposite over adjacent. I'm running out of time. We're going to have to do this fast. 800 tangent 34. So A would be 539.6068135. I'm not going to round yet. I'll wait around at the very end. So that's this distance here. Now look at the big right triangle. It still has the 800, but the angle is 39 degrees. I'm going to draw it all in pink here. 39 degrees. I'll call that B. Now I'm going to subtract those to get that distance there. This is 800. Still opposite over adjacent. Multiply both sides by 800. That's going to get you B, and then subtract this number. So 800 tangent 39. Now don't get carried away now that I've shown you the degrees and minutes mark. You don't need to be hitting the degrees as long as you have it set in degree mode, unless it says degrees and minutes. If you just put 39, it's going to assume degrees. So 647.8272266. And now I'm going to subtract those two numbers, and that'll get me this high. So I'll say minus 539.6068135. So what are we getting there? 108.22. Oh, let's see. Uh-oh. Look at what I did. I've run out of time, but you'll notice I consistently read this 37 as if it were 39. Now, y'all can't do this in your homework. You've got to make sure you have the right angle. But I worked it as if that were 39 degrees. Okay? So let's assume it's a 39. I don't know why my vision, I guess my vision's getting worse and worse as I get older. That angle right there was actually 37, but I used 39 throughout all of this. And so let's just say, this is just an example. So I worked it as if the angles of elevations were 34 degrees and 39. If you spotted that 37, then you have better vision than me, which isn't saying much. So 108.22, do you all see what I did there? I subtracted this and that. Okay. Get this distance right here. But we're out of time right now, so no more time for me to do any more examples. Hopefully this is enough for you to do it. Start going on your homework. These are some nice applications of right triangle trigonometry. Okay, bye-bye.